Target destroyed.
Russia has accused Ukraine of launching an attack on one of President Vladimir Putin's residences.
On January 27th, a lone Ukrainian drone penetrated Russian-controlled airspace with a singular purpose. Its mission wasn't to destroy a runway or ignite fuel tanks. Its task was far more precise, surgical. Somewhere ahead lay Russia's most critical airborne sensor platform in the south. An aircraft that controlled detection, tracking, and early warning across the entire Black Sea. If it remained operational, Ukraine would lose its blind spot. If it didn't, the balance of power would shift subtly, yet decisively. The target was an IL-38N, Russia's most capable maritime reconnaissance aircraft operating in the southern theater. It wasn't designed to strike, but to see, and seeing controlled everything that followed. Welcome to Border Watch Daily, where we decode complex military operations and their strategic implications. Stay with us, as what's coming next will reveal an unexpected flaw in Russian defenses. This platform integrated radar tracking, electronic intelligence, magnetic anomaly detection, and sonar processing into a single operational picture. During one patrol cycle, it could monitor up to 46 contacts simultaneously, extending Russian situational awareness over 300 kilometers beyond the coast. If activated, long-range Ukrainian drones would be detected earlier. Naval logistics routes would be exposed. Low-altitude penetration corridors would effectively vanish. Intelligence assessments showed that a single uninterrupted mission could compromise assets worth over $4 billion. Such a risk was unacceptable. Satellite imagery taken earlier that morning confirmed intense pre-flight activity. Engine cowlings had been removed. Refueling vehicles were positioned along the tarmac. Maintenance crews had begun final system checks. Under standard procedures, the aircraft would be ready for mission launch in under 90 minutes. Beyond that point, engagement options would collapse. The airbase was protected by multi-layered air defense systems. Interceptor aircraft remained on alert. Any strike launched after takeoff would face detection within minutes and interception soon after. This operation was not about destroying an aircraft airframe, but about neutralizing a system. Damaging the fuselage would have served no purpose. Neutralizing the mission architecture, however, would shift the balance of the southern battlefield. If the IL-38N entered service, Russia would regain full aerial awareness of the region. If it didn't, Ukraine would temporarily, yet critically, retain its operational blind spot. The decision was already made. Only execution remained. The chosen platform was the jet-powered Ludi drone. It wasn't selected for stealth, but because nothing else could reach the target in time. The Ludi operated without live control. No joystick, no satellite link, no video feed. After launch, the aircraft followed a fixed mission program stored in its flight computer. This choice was forced. The density of electronic warfare along the southern front had significantly increased. Remote control links now survived for less than 10 seconds before collapsing. Any drone relying on constant communication would be neutralized almost immediately. The Ludi eliminated this weakness. The drone cruised at 205 kilometers per hour, maintaining an altitude between 30 and 60 meters. At this level, the probability of radar detection dropped below 5% beyond coastal range. The planned route extended 610 kilometers. Fuel reserves allowed for only 6 minutes of deviation. A single navigation error would end the mission. There was no secondary drone on standby. Production capacity remained limited. Each unit required over 1,200 hours of assembly, and the system cost exceeded $430,000. Consumable in theory, rare in reality. The payload was designed for a single task. Its warhead produced a focused fragment field, capable of disabling hardened avionics in less than 4 milliseconds. This was not a warning strike, nor a message, nor a demonstration. It was a single-use operation with only one acceptable outcome. If the Ludi failed, the IL-38N would fly. If the aircraft flew, Ukraine's southern airspace would no longer be blind. The launch decision was final. The next problem was physical. Russian air defense coverage in the south appeared dense. Over 1,200 radar systems were deployed, from the coast to inland positions. On planning maps, no gaps existed. In practice, the gaps were fundamental. Radar energy travels in straight lines. The Earth, however, is not flat. Most coastal radar antennas were mounted between 18 and 25 meters above the ground. From this height, the radar horizon extended approximately 40 kilometers. Any object flying below 50 meters disappeared beyond that limit, regardless of the system's power. At 10:42 local time, the Ludi crossed the coast and stabilized at an altitude of 35 to 45 meters. 6 minutes later, it vanished. The probability of detection dropped to nearly zero, not reduced, but eliminated. Even systems capable of tracking fighter jets at 300 kilometers were blind. Increasing output power changed nothing. The beam passed overhead, never touching the target. Russian operators continued to scan. Their screens were filled with ground returns, sea clutter, and atmospheric interference. The drone was already inside protected airspace, advancing at 205 kilometers per hour for over 70 minutes. No radar could reacquire it. This wasn't stealth technology. The aircraft wasn't hidden. It was simply below the line of sight. While command centers searched at higher altitudes, the battle progressed beneath their noses. Sensors obeyed geometry, not urgency. During this window, Russian air defense lost control of the aerial picture. The Ludi advanced untouched, not because it was superior, but because the planet itself blocked any attempt to see it. The nature of combat had changed, and radar was no longer part of it. At 10:58 local time, Russian air defense command centers confirmed complete radar loss of the target. Several systems were still transmitting. Antennas remained active. Screens displayed normal background returns, but the trace had vanished. No altitude data, no range correlation, no confirmed radar contact. The disappearance followed a known pattern. Very low-flying targets regularly passed below the radar horizon. This time, Russian command didn't wait. Across the entire southern region, a secondary detection layer was activated, the Acoustic surveillance network. Over 200 passive listening stations were positioned at intervals of 3 to 5 kilometers, covering routes that radar couldn't reach. These sensors emitted nothing, they listened. Each unit combined multi-directional microphones with onboard processors trained to classify engine noise. Propellers, helicopters, and piston engines produced predictable acoustic signatures. Jet engines were different. The Ludi's turbofan generated dominant frequency peaks between 4 and 8 kilohertz, associated with a low-frequency combustion band below 500 Hz. Cold air increased sound transmission efficiency, extending detection range by nearly 30%. Within minutes, one station detected an anomalous signal well above ambient background levels. Additional sensors confirmed corresponding bearings. The network fused the data. The trace reappeared, not on radar, but by sound. Positional accuracy tightened to within 40 meters, with updates every few seconds. For the first time since it crossed the coast, the drone could be tracked again, but only tracked. The acoustic system could calculate heading and speed. It could warn defensive units. It could not engage. Russia had regained situational awareness, but not control, and the next decision would need to be made quickly. Acoustic tracking data was fed to a Tor M2 battery positioned along the projected flight corridor. The stream provided updates on bearing, speed, and predicted trajectory every few seconds. The system was designed to counter low-altitude threats. The Tor M2 could engage cruise missiles, helicopters, and aircraft using radar-guided interceptors. Its fire control radar was capable of tracking dozens of objects simultaneously under normal conditions. The limitation was elevation. The radar required a minimum angle of approximately 3 degrees to separate targets from terrain reflections. Below that, ground clutter saturated the signal processor. The Ludi maintained its flight at approximately 30 meters. At a distance of 16 kilometers, this altitude produced an elevation angle of about 1 degrees. The radar beam intersected the terrain before reaching the aircraft. The screen showed interference, false returns, no valid target. Operators increased output power and tightened the search sector. The effect was negligible. To detect an object at this altitude, the Tor M2 required it to be within about 1 kilometer. At the drone's speed, the engagement window lasted less than 20 seconds, and only if the aircraft approached directly. This was not the case. The drone traversed laterally, passing north of the battery. Acoustic updates confirmed the geometry. The range briefly decreased, then began to increase again. Radar lock was never achieved. Missiles remained ready. The launcher remained active. Procedures were followed correctly. The system functioned as designed. The Tor M2 could not engage a target that existed below its usable radar horizon. The drone exited the defended area untouched. Russia possessed detection and firepower. What it lacked was an exploitable line of sight. This failure forced command to consider a far riskier solution. The Tor M2 failed to engage. Radar lock was never achieved. With a drone already beyond the defended area, Russian command faced a rapidly shrinking set of options. Only one remained. An improvised interceptor was launched, a Garand drone equipped with a Verba Manpads system. The configuration was non-standard. The Garand was designed as a one-way attack drone, not an air defense platform. Mounting a surface-to-air missile required external mounts, slave triggers, and exposed wiring along the fuselage. The modification added 14 kilograms. This increase reduced endurance by over 60%. Maximum flight time dropped below 80 minutes. Control margins narrowed. Stability degraded. There would be no reload. The Verba missile offered high lethality under correct conditions. Its seeker combined infrared, ultraviolet, and near-infrared channels, allowing discrimination against flares and background clutter. Against aircraft, the probability of kill exceeded 0.8. The challenge was interception. The Garand cruised at approximately 175 kilometers per hour. The Ludi moved faster by over 30 kilometers per hour. A direct chase was impossible. Command relied on acoustic tracking data to predict a crossover point rather than chasing the target. Timing became critical. Few reserves allowed for less than 15 minutes of maneuvering. Each correction reduced the remaining margin. An error would mean exhaustion before contact. This was no longer multi-layered air defense. It was a single drone carrying a single missile launched against a faster target already deep inside contested airspace. Russia was no longer reacting with doctrine, but with necessity. Interception would succeed or fail within minutes, and there would be no second attempt. The interception began near the predicted crossover point, as acoustic tracking confined the Ludi to a narrow engagement corridor. The Garand adjusted its heading and descended to reduce background interference, relying on estimated position rather than visual certainty. Contact occurred briefly as the drone crossed open ground during a terrain transition. The exposure window lasted less than 3 seconds, but it was enough. The Verba Seeker activated. Thermal contrast exceeded the background by over 350 degrees Celsius. Infrared and ultraviolet channels confirmed correlation. The target was classified as valid. Launch authorization was transmitted, and the missiles separated cleanly from the rail, accelerating beyond 20 G. The closing rate exceeded 800 meters per second. Estimated time to interception was 11 seconds. From that moment, control ceased. The missile followed proportional navigation, calculating interception geometry internally. No operator intervention could alter its trajectory. The Garand could not guide it. The Ludi could not evade it. The drone carried no countermeasures, no flares, no jamming, no warning system. Its flight computer automatically executed the next waypoint, commanding a steep descent to preserve terrain masking, oblivious that a missile was approaching from above. The Verba followed. Guidance commanded a dive as altitude rapidly collapsed. The missile traversed below 30 meters, entering an area saturated with magnetic interference from the ground, buried metals, and infrastructure debris. The rocket's logic began evaluating proximity cues under degraded conditions. At 9 seconds, the system hesitated. At 11 seconds, detonation occurred. The explosion failed to intercept the target. Fragmentation struck the terrain instead. The Ludi passed through the shockwave without structural damage. The missile was gone. Fuel remained. The drone continued to advance. The interception window closed, not by order, but by the laws of physics. The interception's failure did not alter the mission. The Ludi continued to advance under autonomous control, entering the final phase of the operation. Human intervention was no longer possible. Target selection had fully transitioned to onboard systems. The drone approached an airfield containing several aircraft with nearly identical configurations at low altitude and a shallow angle. Visual similarity made manual identification impossible. This moment had been anticipated. The flight computer activated its trained recognition model. The system had been built using over 4,900 labeled reference images, compiled from satellite data, reconnaissance footage, and verified aeronautical archives. The algorithm didn't look for aircraft by name. It looked for their structure. Video frames were processed at 29 frames per second. Edge patterns, shadow geometry, surface interruptions, and proportional spacing were continuously extracted. Candidates were filtered by engine count, wing location, and fuselage length. One characteristic remained decisive: the E-lint pod, mounted above the aircraft's forward section. This rectangular module altered airflow, shadow shape, and silhouette profile. The standard IL-38 did not possess this structure. The system compared the observed geometry to train parameters in real time. As alignment improved, uncertainty collapsed. Competing aircraft were automatically discarded. No confirmation request was sent. No human review occurred. Once identification confidence exceeded the programmed threshold, The navigation system accepted the result and generated a dedicated attack corridor. All other aircraft on the tarmac were excluded from the strike envelope. This was no longer surveillance, it was selection. The decision was not emotional, it was purely mathematical. The target had been isolated. From that moment, nothing on the ground could redirect the drone. At 12:15 local time, the attack profile shifted. The Ludi did not aim for the fuselage or engines. Its guidance system selected a narrow impact corridor above the aircraft's forward section. This was intentional. Destroying the airframe was pointless. Eliminating the mission system was the objective. The warhead was configured for an airburst detonation, triggered by a radar altimeter calibrated to activate approximately 5-6 meters above the surface. At this height, the blast pattern moved downward rather than outward. Inside the forward section, the charge was surrounded by nearly 1,900 pre-formed steel fragments, each designed for controlled dispersion. Upon detonation, the fragments accelerated to over 1,600 meters per second, traversing the engagement distance in just over 3 milliseconds. The strike cone measured approximately 4 meters in diameter. This area covered the Elan pod and the forward mission bay. The aluminum skin offered no resistance. Sensor housings burst instantly. Antenna arrays were shredded. Processing racks collapsed under a fragment density exceeding 40 impacts per square meter. The aircraft did not explode. Fuel tanks remained intact. Structural integrity remained largely preserved. From the outside, the platform appeared to have survived. Internally, it was annihilated. The central mission computer that fused radar, acoustic, and electronic data was destroyed before it could even register the failure. Data pathways ceased. Screens went black. The aircraft could still fly. It could still land. But it could no longer see, hear, or interpret the battlefield. The platform remained alive. The system, however, did not. In less than 4 milliseconds, Russia lost its southern airborne sensor node, not through outright destruction, but through surgical neutralization. The impact wasn't immediate on the tarmac. It first appeared on operational maps. Within hours, Russian command centers reported a collapse in aerial situational awareness across the entire southern sector. Long-range tracking coverage over the Black Sea dropped by over 60%. Data streams once fused into a single operational picture, fractured into isolated fragments. Naval patrol schedules were suspended. Drone launch warnings no longer arrived in time. Several planned sorties were delayed or canceled due to uncertainty rather than enemy fire. The aircraft itself remained physically present, but its function had vanished. Without the IL-38N's mission system, radar returns could no longer be correlated with electronic intercepts. Sonar and magnetic data lost their context. Targets appeared, vanished, then reappeared without classification. Russian crews reverted to ground-based sensors, reducing effective detection range by over 70%. What had been a multi-layered surveillance network became a collection of blind spots. Restoring capability was not a matter of repair. Replacing the destroyed electronics required factory-level reconstruction, specialized components, and months of calibration. Estimates place recovery time between 6 and 9 months, assuming uninterrupted supply. During this window, the southern battlefield remained partially opaque. The aircraft survived. The system, however, did not. And in modern warfare, losing vision is often more dangerous than losing firepower. This operation was not about destroying an aircraft. It was about removing vision, awareness, and control from the battlefield. No explosions dominated the footage. No spectacular fireballs marked the strike. Yet, the outcome reshaped an entire sector of the war. A single autonomous drone disabled a system worth hundreds of millions of dollars and forced months of strategic adjustment. This is how modern conflict operates today. Silent, precise, and ruthless.